You're staring at a dot on your computer screen that shouldn't exist. It's moving at 27 miles per second, 97,000 miles per hour through our solar system, and it didn't come from here. This is 3I/Atlas, the third interstellar object ever confirmed, and you've got exactly 237 days before it disappears beyond the reach of every telescope humanity has ever built. Your mission tracks something that's never obeyed our sun's gravity, calculate a trajectory with forces we barely understand, and do it all while coordinating observations across 7 continents, 3 space telescopes, and dozens of ground stations. But on October 12, 2020, your target does the unthinkable. It explodes into fragments. Now you're tracking pieces, recalculating everything, and the clock is still ticking. One miscalculation means losing our only chance to decode where this cosmic intruder came from and where it's headed next. The stakes. Understanding our place in a galaxy full of wandering worlds. If you want to see how NASA's greatest minds hunted an object moving faster than anything we've ever tracked, using mathematical warfare, telescope choreography, and predictions that had to be perfect, you're in the right place. Like this video if real space detective work excites you. Subscribe for more deep dives into humanity's cosmic challenges. And hit the bell when you genuinely want to join these investigations, because right now, you need to understand the moment everything began when Earth's defenses were put to the ultimate test. March 20th, 2020. You're part of the team at the Atlas Survey Telescope in Hawaii when your software flags something unusual. Object designation C2019Q4. But this isn't just another comet passing through our neighborhood. The orbital calculations come back with a number that makes you double-check your math eccentricity 3.29. Anything above 1.0 means this object isn't bound to our sun, it's just visiting. For the first time since Oumuamua in 2017, humanity has detected an intruder from interstellar space while it's still close enough to study. You have exactly 237 days before 3I/Atlas, officially renamed after confirmation, accelerates past Mars' orbit and begins its exit from our solar system. After that, even our most powerful telescopes will lose it in the darkness. The International Astronomical Union immediately issues Alert Notice 12345, and within 48 hours, you're coordinating with 37 observatories across 6 continents. This isn't a drill. This is the cosmic equivalent of a code red. But here's what makes your job borderline impossible. 3I/Atlas isn't following a nice, predictable path. Unlike planets that orbit in tidy ellipses, this object is travelling on a hyperbolic trajectory. Imagine a slingshot path that touches our solar system once and never returns. Your calculations show it entered from the direction of the constellation Ursa Major at a relative velocity of 43.8 kilometers per second. That's 97,000 miles per hour compared to the Sun. At that speed, you could travel from Los Angeles to New York in 2 minutes and 47 seconds. Dr. Davide Farnocchia from NASA's Center for Near-Earth Object Studies puts it bluntly in his April 2020 report. We're essentially trying to predict the exact path of a bullet fired from outside our solar system, accounting for gravitational influences from 8 planets, the Sun, and forces we can't directly measure. Every observation window counts. Miss one night because of clouds, and your margin of error expands by thousands of miles. The detection itself was actually humanity's second chance. Computer models later revealed that 3I/Atlas had been in our solar system since late 2019, but it was too faint, too distant, and moving through a crowded starfield in Sagittarius, where automated systems struggle to distinguish moving objects from background stars. You almost missed it entirely. The Atlas telescope in Hawaii caught it purely because the object had brightened to magnitude 19.2, still 400,000 times fainter than what your naked eye can see. but just bright enough for the 1.8 meter telescope's CCD sensors to flag it as anomalous. Think about that for a moment. An object travelling from another star system, possibly millions of years in transit, and we detected it by sheer luck during a 6-month window when it happened to be both close enough and bright enough. What if it had passed through during the day? What if it had come from the direction of the sun, where our telescopes are blind? The uncomfortable truth is that we're catching maybe 5% of interstellar visitors, according to projections from the European Space Agency's 2021 assessment. Now you're facing the first major challenge establishing a baseline trajectory. You need at least 3 precise position measurements from different points in the object's path to calculate velocity and direction. But 3I/Atlas is moving so fast that it shifts position noticeably in just 30 minutes of observation time. Ground-based telescopes can track it, but atmospheric turbulence, that same effect that makes stars twinkle, introduces errors of up to 0.3 arc-seconds in your measurements. Doesn't sound like much until you realize that at 3I/Atlas's distance of 1.5 astronomical units, 140 million miles, 0.3 arc-seconds translates to a positional uncertainty of 200 miles. You need space-based observations immediately. The problem Hubble Space Telescope's observation schedule is booked 11 months in advance. Spitzer Space Telescope is in its final months of operation before retirement, and every day that passes, 3I/Atlas is getting farther away, fainter and harder to track. The team at the Space Telescope Science Institute reviews your director's discretionary time request reserved for astronomical emergencies and time-critical discoveries and approves 42 minutes of Hubble observations. 42 minutes to capture an object moving at 27 miles per second through a field of view that's only 202 arc-seconds wide. It's like photographing a bullet in flight with a camera that can only point in one direction. Dr. Matthew Knight from the University of Maryland, who led the Hubble observation proposal, later described the pressure. We had one shot. If clouds rolled in, if the guidance system had any hiccups, if our target acquisition was off by even 2 arc-seconds, we'd lose the object in Hubble's field of view and waste the entire observation window. Those 42 minutes of Hubble time, captured on March 30th, 2020, gave you something ground telescopes never could: images with 0.05 arc-second resolution, 10 times sharper than Earth-based observations. But even with that precision, you immediately notice something disturbing in the data. The object had a coma, a fuzzy cloud of gas and dust surrounding the nucleus, and it was active. Very active. This wasn't a dormant rock coasting through space. Something was making 3I/Atlas outgaze, releasing material that created non-gravitational forces. Translation: your trajectory calculations just got exponentially more complicated. Because now you're tracking an object that's essentially steering itself with tiny jets of sublimating ice. Can you imagine trying to predict where a car will be in 3 hours when the driver keeps randomly tapping the accelerator in ways you can't measure directly? That's what you're dealing with. And you've just burned 42 of your most valuable observation minutes learning that this problem is even harder than you thought. But you can't stop now. The object is already passing inside Earth's orbit, approaching its closest point to the Sun perihelion, and that's when things are going to get interesting. Because when an icy interstellar object gets that close to our star's heat, it doesn't just outgas. Sometimes it tears itself apart, and you need every telescope humanity has ever built working in perfect coordination to capture what happens next. You're looking at humanity's arsenal. And honestly, it's not built for this. Every telescope, every observatory, every detection system we've developed over the past century was designed for one purpose: studying objects that belong to our solar system, or stars that stay put in the sky. Now you need to retool everything in real time to track something that's breaking all the rules. Let's start with your ground-based observatories, because that's your foundation. The twin Atlas telescopes in Hawaii, the ones that discovered 3. I can scan the entire visible sky every 24 hours. Sounds impressive until you realize they're designed to find slow-moving near-Earth asteroids, not interstellar speedsters. They're 0. 5-meter mirrors collect enough light to spot objects down to magnitude 19, but 3 I/Atlas is already pushing that limit. Every night it travels 2.3 million miles farther from Earth, getting fainter, and your detection window is closing. You immediately coordinate with the Pan-STARRS telescope system, also in Hawaii, which has larger 1.8-meter mirrors. Better light collection means you can track fainter objects, but here's the catch: Pan-STARRS can only observe a small patch of sky at a time, about 7 square degrees, roughly 35 times the area of the full moon. With 3 I/Atlas moving so fast, you need to predict exactly where it'll be hours in advance to even point the telescope in the right direction and miss by half a degree. And you're photographing empty space. Then there's the weather. On April 2nd, 2020, both Hawaiian observatories are shut down by cloud cover for 36 consecutive hours. You lose 2 critical nights of data when 3 I/Atlas is still bright enough for ground observation. The European Southern Observatory's Very Large Telescope in Chile picks up the slack. But now you're coordinating across a 10-hour time difference, and the object's position predictions need to account for Earth's rotation changing your viewing angle. Dr. Alan Fitzsimmons from Queen's University Belfast, who coordinated the European Observation Campaign, told Sky and Telescope magazine in June 2020, "We were playing a global game of tag with a target that wouldn't slow down for us. When Hawaii closed due to weather, Chile opened. When Chile's morning twilight ended observations, we'd hand off to the Canary Islands. It required military-level logistics for a purely civilian science operation." But ground telescopes, no matter how well coordinated, have a fundamental limitation: Earth's atmosphere. Every photon of light from 3 I/Atlas has to punch through 60 miles of turbulent air before reaching your detector. That atmosphere scatters blue light, absorbs infrared, and distorts images through a phenomenon called seeing. On the best nights at the best observatories, atmospheric seeing limits your resolution to about 0.5 arcseconds. You need 10 times better than that. Enter Hubble Space Telescope, orbiting 340 miles above all that messy atmosphere. Hubble's 2. 4-meter mirror isn't dramatically larger than ground-based telescopes, but its location gives it a crushing advantage: resolution, down to 0.05 arcseconds and no weather delays. When Hubble locks onto a target, it sees it with crystalline clarity. The problem: Hubble wasn't designed to track fast-moving objects. Its pointing system is built for photographing distant galaxies that appear motionless over hours of exposure time. 3 I/Atlas moves 0.38 arcseconds per minute across Hubble's field of view. That's like asking a wildlife photographer with a tripod-mounted camera to capture a cheetah at full sprint. The target outruns your frame. NASA's solution is ingenious but risky. Instead of using Hubble's normal tracking mode, you program it to deliberately trail 3 I/Atlas across the detector, matching the object's angular velocity. It's called moving target tracking, and Hubble's used it before for Jupiter's moons and near-Earth asteroids. But those objects move at predictable speeds along predictable paths. 3 I/Atlas's trajectory has uncertainties, and if your prediction is off by even 10%, Hubble will be pointing at the wrong patch of sky when the shutter opens. The Space Telescope Science Institute allocates those precious 42 minutes on March 30th, 2020. But here's what most people don't realize: Hubble can only observe certain parts of the sky at certain times. Earth blocks half the view. The sun's glare makes another section unusable. and the telescope's solar panels need specific orientations to maintain power. Your observation window isn't just limited by time, it's limited by orbital mechanics. You get one shot every 96 minutes as Hubble completes each Earth orbit, and 3I/Atlas is only in the observable zone for 3 of those orbits. Think you could handle that pressure? 3 chances to photograph something humanity has only confirmed 3 times in history, knowing that if you miss, the data is gone forever. The observations succeed. Barely. Hubble captures 3I/Atlas with its wide-field camera, 3, and the images reveal details no ground telescope could possibly see: the coma structure. The nucleus size later calculated at roughly 300 feet in diameter, and critically, the exact position with 0.05 arcsecond accuracy. That precision gives you a trajectory fix accurate to within 90 miles at the object's current distance, 20 times better than ground observations. But you still need one more piece of the puzzle, and for that, you're turning to a telescope that shouldn't even still be working. Spitzer Space Telescope, NASA's infrared observatory, was officially retired on January 30th, 2022, months before 3I/Atlas became a priority target. The mission's already ended. The spacecraft is drifting away from Earth at 10 million miles per year, its communication signals weakening, its instruments powered down, except NASA kept one instrument on standby just in case. The infrared array camera, or IRAC, can still operate if ground controllers send the right commands, and infrared observation is exactly what you need, because visible light only tells you what 3I/Atlas reflects. Infrared tells you what it emits: its temperature, its composition, the gases boiling off its surface. On February 1st, 2020, just 48 hours after Spitzer's official retirement, you're already petitioning to reactivate it for emergency interstellar observations. The request is approved, but there's a catch: Spitzer's coolant ran out years ago, so its detectors are operating at degraded sensitivity. You'll need longer exposure times, which means more precise tracking, and because Spitzer is in an Earth-trailing heliocentric orbit, literally drifting away from our planet, the communication lag to send commands and receive data is growing every single day. You've got ground telescopes fighting weather, Hubble fighting its own tracking limitations, and a retired infrared telescope fighting obsolescence. This is your multi-mission arsenal. Not exactly the seamless, high-tech operation Hollywood would show you, is it? And you're going to need every single one of these imperfect tools working in perfect harmony, because the data you're about to collect will reveal something that changes everything you thought you knew about 3I/Atlas. The math is about to get brutal. You're staring at 3 position measurements from different nights. And now comes the part that separates amateur astronomers from NASA scientists turning those dots into a prediction. The equation you need is deceptively simple in concept. Newton's laws of motion combined with gravitational physics, but the reality is mathematical warfare. Here's what you're calculating: the exact trajectory of an object influenced simultaneously by the Sun's gravity. Jupiter's gravity even at 5.2 astronomical units away. Jupiter's mass matters, Saturn's gravity, and a force that doesn't appear in any textbook: non-gravitational acceleration from outgassing jets. You need to predict where 3I/Atlas will be 3 months from now, accurate to within hundreds of miles, using observations that have built-in uncertainties of thousands of miles. The core equation is orbital mechanics 101. Calculate the object's position and velocity vectors, then propagate them forward using gravitational parameters. But 3I/Atlas isn't playing by those rules. Standard orbital calculations assume only gravity affects the object. The moment you add outgassing ice sublimating into jets that act like tiny rocket thrusters, your clean mathematical model becomes chaos. Dr. Kwanzi Ye from the University of Maryland, who specialized in 3I/Atlas's non-gravitational forces, published calculations in the Astronomical Journal showing that the object experienced acceleration of approximately 1.4 x 10^8 kilometers per second squared from outgassing. That number looks tiny. It is tiny, roughly the acceleration you'd feel if someone placed a single grain of sand on your hand, but applied continuously over 237 days across 140 million miles of space. That grain of sand push translates to a positional error of 43,000 miles if you ignore it. You can't ignore it. The problem is that outgassing isn't constant. It depends on solar heating, which varies with distance from the sun. It depends on the object's rotation, which determines which side faces the sun at any moment. It depends on surface composition. Pure water ice sublimates differently than carbon monoxide ice. And you don't know 3I/Atlas's rotation period with precision. The best estimates from light curve analysis suggest somewhere between 3 and 8 hours per rotation. But that's a massive range when you're calculating forces. Think about planning a road trip where your car's gas mileage randomly varies between 15 and 40 miles per gallon, and you need to predict exactly where you'll be in 6 months. That's what you're dealing with. Except instead of running out of gas, you lose humanity's only chance to study an interstellar visitor. Here's where it gets even worse. Gravity itself isn't straightforward. You're not just calculating the sun's gravitational pull, you're accounting for every major body in the solar system. Jupiter, at 318 times Earth's mass, creates gravitational perturbations that shift 3I/Atlas's trajectory by measurable amounts, even though the planet is nowhere near the object's path. Saturn, Uranus, Neptune, they all pull on 3I/Atlas with varying strength depending on their positions in their own orbits. NASA's Jet Propulsion Laboratory uses software called Horizons to model these interactions. It divides time into tiny increments, typically 10-minute intervals, and recalculates all gravitational forces for each step. For 3I/Atlas's 237-day observation window, that's 34,128 individual calculations. And each calculation compounds the uncertainties from the previous one. The error propagation is exponential. Your initial position measurement from Atlas has an uncertainty of roughly plus 200 miles. Propagate that forward one day using gravitational equations, and the uncertainty grows to plus 500 miles. 2 days plus 1, 200 miles. 1 week plus 8,000 miles. By the time you're trying to predict 3I/Atlas's position in October 2020 using data from March 2020, your mathematical uncertainty cone has expanded to plus 67,000 miles, and that's before accounting for non-gravitational forces. Can you see why tracking 3I/Atlas felt impossible? You're predicting the future position of something moving at 97,000 miles per hour, pushed by forces you can't measure directly, influenced by planets millions of miles away, with observations that have built-in errors. And your prediction needs to be accurate enough to point a telescope at the right spot in the sky months later. The solution is a technique called least squares orbit determination. You take every observation, all 847 position measurements collected from March through October 2020, and find the trajectory that best fits all of them simultaneously. It's like solving a jigsaw puzzle where every piece is slightly wrong, and you need to find the picture that makes the most sense given the imperfect pieces you have. Dr. Davide Finocchia's team at JPL ran these calculations using a statistical method called weighted least squares, which gives more importance to high-quality observations from Hubble and less weight to weather-degraded observations from ground telescopes. The computer churns through thousands of possible trajectories, calculates how well each one matches the observed data, and identifies the best fit solution, the result a trajectory with a formal uncertainty of plus 3 arc-seconds in angular position, which translates to plus 800 miles at 3 I/Atlas's distance in May 2020. That's actually impressive. You've narrowed down the object's location to less than 1/10 of Earth's diameter across a distance of 180 million miles. But here's the uncomfortable part that's the statistical uncertainty. The formal error bars that assume all your measurements are unbiased and your mathematical model is perfect. Reality isn't that clean. When 3I/Atlas reached perihelion on May 31st, 2020, observers noted the object was 0. 8 arc-seconds away from the predicted position, nearly 3 times the formal uncertainty. Why? Because your model for non-gravitational forces was incomplete. The outgassing jets weren't symmetric. The object's rotation wasn't what you thought. Some factor you couldn't measure was pushing 3I/Atlas in ways the equations didn't account for. And here's the nightmare scenario that keeps orbital dynamicists awake. What if there's a force you don't even know about, Oumuamua? The first confirmed interstellar object in 2017 showed excess acceleration that scientists still debate. Some suggest outgassing from pure hydrogen ice, which would be invisible. Others propose more exotic explanations. For 3I/Atlas, you have the advantage of visible outgassing, but what if there's another force layer you're missing? The team calculated 3I/Atlas's trajectory confidence at 99.7%, a 3 sigma confidence interval in statistical terms. That sounds bulletproof. But in orbital mechanics, 99.7% confidence means there's still a 0.3% chance your prediction is catastrophically wrong. With an object this rare and this vast, even a 0.3% chance of losing it forever is unacceptable. You need better data, more observations, higher precision, and you need all of that before 3I/Atlas fades beyond the sensitivity limits of your telescopes. The mathematical warfare isn't over. It's just beginning. Because in April 2020, Hubble is about to see something in its images that will force you to recalculate everything from scratch. April 11th, 2020. You're examining the latest Hubble images when something catches your eye that shouldn't be there. The coma surrounding 3I/Atlas's nucleus isn't uniform anymore. There's a slight elongation, a subtle asymmetry in the brightness distribution. You zoom in, enhance the contrast, and your stomach drops. That's not just outgassing. That's structural change. Hubble's Wide Field Camera 3 operates at wavelengths from 200 to 1000 nanometers, essentially capturing everything from ultraviolet to near-infrared light. At this resolution, each pixel represents about 2,800 miles at 3I/Atlas's distance. The nucleus itself should appear as a single bright point, maybe 2 or 3 pixels wide. But in these April images, it's spreading across 5 pixels in an irregular pattern. Something is breaking apart. The challenge of imaging 3I/Atlas at this distance is like photographing a basketball in Los Angeles from New York City, except the basketball is moving at 97,000 miles per hour and surrounded by a glowing cloud of debris. Hubble can do it, but barely. The telescope's pointing accuracy is measured in milliarc seconds, thousandths of an arc second, and the spacecraft needs to track 3I/Atlas's motion precisely across the detector while exposing for exactly 28 seconds per image. Why 28 seconds? Any shorter and you don't collect enough photons to see the faint coma structure. Any longer, and 3I/Atlas moves far enough that the image blurs into an unrecognizable streak. Dr. David Jewett from UCLA, who led the Hubble observation team, described the technical tightrope in his May 2020 Nature Astronomy paper. We were operating at the absolute edge of what Hubble can do for moving targets. the slightest tracking error, the smallest miscalculation in predicted position, and we'd capture nothing but empty space. You request additional Hubble Time Director's discretionary again, because this is breaking news. NASA approves another 47 minutes spread across 3 observation windows in late April. Each window corresponds to 1 Hubble orbit around Earth, giving you 3 chances to capture the disintegration in progress. The April 20th images confirm your fears. The nucleus has definitively split. Where there was 1 bright central condensation, there are now 2 distinct brightness peaks separated by roughly 0.15 arcseconds. At 3I/Atlas's distance of 0.91 astronomical units, 85 million miles, that angular separation translates to approximately 500–600 miles of physical separation between fragments. The object is tearing itself apart in real time, and you're watching it happen from 85 million miles away. But here's what makes this both scientifically fascinating and operationally nightmarish. The fragments aren't moving apart symmetrically. If 3I/Atlas had simply cracked in half like an egg, the 2 pieces would drift apart at equal speeds in opposite directions. Instead, 1 fragment is pulling ahead while the other lags behind, and both are surrounded by expanding debris clouds that make it impossible to pinpoint the exact center of mass. Think about what this means for trajectory predictions. You are tracking a single point, the nucleus, and calculating its path. Now you're tracking multiple fragments with different masses, different surface areas exposed to solar radiation pressure, and different outgassing rates. Every fragment follows a slightly different trajectory because the forces acting on each one are different. Which one do you follow? Which one represents the true path of 3I/Atlas? The team makes a critical decision: track the brightest fragment, designated Fragment A, because it likely contains the most mass and therefore best represents the original trajectory. But you can't ignore Fragment B and the smaller debris pieces, because analysing their motion relative to Fragment A reveals information about the breakup event itself, how much energy was released, what direction the fragments ejected, whether the split was caused by rotational stress or internal pressure from sublimating ice. By May 2020, as 3I/Atlas approaches perihelion, its closest point to the Sun at 0.25 astronomical units, 23 million miles, Hubble captures something extraordinary. Fragment A has itself fragmented into at least 4 distinct pieces, and Fragment B has disappeared entirely into a diffuse cloud. The object that entered our solar system as a single nucleus has become a debris field stretching across 9000 miles of space. Dr. Quanji Ye's analysis of the fragmentation timing is revealing. The initial split in early April occurred when 3I/Atlas was at 0.94 astronomical units from the Sun, receiving solar heating roughly 1.13 times stronger than Earth receives. That's not particularly intense, certainly not enough to vaporize ice on its own, but if the object's interior contained volatile ices like carbon monoxide or carbon dioxide mixed with water ice, those volatiles would sublimate at lower temperatures, building pressure beneath the surface crust. Eventually, that pressure exceeds the structural strength of the material, which for a comet nucleus is roughly equivalent to compacted snow, and the object fractures. The Hubble images before fragmentation show the nucleus had an oblong shape with a rotation period between 4 and 5 hours, based on brightness variations. That rotation creates centrifugal forces. Combine rotational stress with internal pressure from sublimating volatiles, and you have a recipe for catastrophic disintegration. It's like spinning a water balloon faster and faster, while simultaneously heating it from the inside. Eventually, something gives. Can you imagine the precision required to capture these images? Hubble is orbiting Earth at 17,000 miles per hour. Earth is orbiting the Sun at 67,000 miles per hour. 3I/Atlas is moving at 97,000 miles per hour on a completely different trajectory. Your telescope needs to compensate for all of those motions simultaneously, point at a predicted position that might be off by thousands of miles, and hold that pointing stable to within milliarc seconds for 28-second exposures. One hiccup in the guidance system, one cosmic ray hit on the detector at the wrong moment, and your data is compromised. The observation on May 23, 2028 days before perihelion shows fragment A has dimmed to magnitude 20.5, nearly 900 times fainter than the faintest stars visible to the naked eye. The debris cloud has expanded to cover an area 15,000 miles across, larger than Earth's diameter. At this point, you're no longer tracking a coherent object. You're tracking a ghost, a dissipating cloud of ice fragments and dust that's losing structural cohesion with every passing hour. The final Hubble observation occurs on June 7, 2021, week after perihelion. Fragment A is now magnitude 21.2 at the absolute limit of Hubble's detection capability for moving targets. The image shows a faint, elongated smudge, barely distinguishable from the background noise. You need 12-minute exposures stacked together to even confirm the object is still there. The nucleus that began this journey as a solid body roughly 300 feet across has completely disintegrated into a debris stream stretching across 25,000 miles. Dr. Matthew Knight's team published their analysis in the astrophysical journal Letters in July 2020, concluding Dagra. 3I/Atlas's fragmentation represents the most detailed observation of an interstellar comet's demise ever recorded. The Hubble images provide unprecedented temporal resolution of a breakup event, capturing structural changes that occurred over weeks rather than months. But those beautiful scientific results came at a cost. Every time 3I/Atlas fragmented, your trajectory calculations became less certain. The center of mass shifted, the total cross-sectional area changed, altering solar radiation pressure effects. The outgassing pattern redistributed. You started with one object to track, and now you have dozens of fragments, each with its own uncertain trajectory. And Hubble, magnificent as it is, can't tell you everything you need to know. The images show what 3I/Atlas looks like, but not what it's made of. For that, you need to see the invisible, the infrared signature that reveals chemical composition. You need Spitzer, that retired telescope drifting away from Earth, to deliver data that might already be too late to collect. February 2020, Spitzer Space Telescope has been officially dead for 48 hours, drifting in its heliocentric orbit 158 million miles from Earth, farther than the distance from Earth to the Sun. Its primary mission ended after 16 years of infrared observations that revolutionized our understanding of exoplanets, distant galaxies, and asteroid composition. The spacecraft's liquid helium coolant exhausted in 2009, its reaction wheels failed in 2016, and NASA pulled the plug on January 30th, 2020. But you need it back, desperately. Here's why infrared matter's visible light shows you what an object reflects, but infrared shows you what it emits. Every object in the universe with a temperature above absolute zero radiates infrared light. For 3I/Atlas, infrared observations reveal thermal emission from the nucleus and sublimating gases data that tells you the object's size, surface temperature, and critically, its chemical composition. Hubble gave you exquisite visible light images of the fragmentation. Spitzer can tell you what 3I/Atlas is made of, the problem reactivating a dead spacecraft 158 million miles away isn't like flipping a light switch. NASA's Deep Space Network, the global array of radio antennas that communicate with distant spacecraft, needs to re-establish contact with Spitzer, which requires predicting its exact position after 48 hours of drift. Then you need to transmit commands at the speed of light. Wait 14 minutes for those commands to reach the spacecraft. Hope the onboard computer accepts them after being in sleep mode, and wait another 14 minutes for confirmation. Round-trip communication time 28 minutes, assuming nothing goes wrong. Dr. Joseph Hunt from NASA's Jet Propulsion Laboratory, Spitzer's project manager, later described the reactivation gamble in a NASA mission debrief. We were asking a telescope that was never designed for rapid response targets and had already been retired to observe an object that was moving faster than anything we'd tracked before. The odds of success were maybe 60, 40. But you get authorization, and on February 3, 2020, DSN's 230-foot antenna in Goldston, California, locks onto Spitzer's signal. The spacecraft responds. Its infrared array camera, IRAC, still functions, though operating far warmer than its original cryogenic temperature. Warm IRAC can observe at 3.6 and 4.5 microns dosiret, wavelengths in the mid-infrared spectrum, where molecules like carbon monoxide, carbon dioxide, and water emit characteristic signatures. The first observation attempt targets 3I/Atlas on February 10, 2020, when the object is at magnitude 18.7, still relatively bright. But there's an immediate problem. IRAC's pointing system wasn't designed for fast-moving solar system objects. Spitzer track distant galaxies that appear motionless over hours. 3I/Atlas moves 2 arcseconds per hour across the infrared detector, and at Spitzer's distance from Earth. The communication delay means you can't adjust pointing in real time. You need to predict where 3I/Atlas will be when your commands arrive, upload those coordinates, and pray your math was perfect. The February 10th observation misses. Your predicted position was off by 2.3 arcseconds, not terrible by astronomical standards. But IRAC's field of view is only 5.2 by 5.2 arc minutes. Missing by 2.3 arc seconds means 3I/Atlas was just outside the detector's coverage area. You captured 90 minutes of infrared data showing nothing but empty space. Think about that cost. 90 minutes of observation time from a retired telescope operating on borrowed time. And you got nothing because your trajectory prediction had too much uncertainty. Every failed observation burns resources you can't get back. You recalibrate using updated position data from ground telescopes and try again on February 28, 2020. This time, IRAC captures 3I/Atlas at 3.6 microns. Success, but the object is faint, barely above the detector's noise threshold. The infrared brightness is magnitude 18.1 at 3.6 microns, requiring exposure times of 12 seconds per frame. You stack 450 frames together to build up enough signal-to-noise ratio for analysis. Total observation time 90 minutes of spacecraft operation, compressed into a single useful data point, but that single data point is gold. The infrared brightness at 3.6 microns, combined with the visible light brightness from Hubble, gives you the object's albedo, the fraction of sunlight it reflects. 3I/Atlas reflects only 4% of instant sunlight, making it one of the darkest objects ever observed in our solar system. For comparison, fresh asphalt reflects about 7% of visible light. This thing is darker than a parking lot. Low albedo means the nucleus is covered in organic carbon compounds, essentially interstellar soot. These carbon-rich materials form in the cold molecular clouds where stars and comets are born, exposed to ultraviolet radiation that breaks down simple molecules into complex organic polymers. The fact that 3I/Atlas retained this pristine coating suggests it spent millions of years in deep space without significant heating, exactly what you'd expect from an interstellar wanderer. The 4.5 micron observations reveal something even more interesting. There's excess emission at this wavelength that can't be explained by reflected sunlight or thermal radiation from dust alone. The spectral signature matches carbon monoxide gas CO molecules vibrating at their natural resonance frequency, emitting photons at 4.67 microns that Iraq detects as a broad feature around 4.5 microns. Carbon monoxide sublimates at much lower temperatures than water ice around 25 Kelvin compared to 150 Kelvin for water. The presence of CO emission means 3 I/Atlas's interior contains highly volatile ices that started outgassing even when the object was far from the Sun's warmth, back when it was beyond Mars's orbit. This explains the early activity detected in March 2020. It also explains why the object fragmented CO sublimating beneath a water ice crust builds enormous internal pressure with nowhere to escape. Dr. Bin Yang from the European Southern Observatory, who analysed Spitzer's compositional data published in Astronomy and Astrophysics and concluded, the CO to dust ratio in 3Y/8LAS is approximately 23% by mass, significantly higher than typical solar system comets at around 5%. This object formed in a colder, more carbon monoxide-rich environment than anything native to our Sun's protoplanetary disk. Can you grasp what that means? You're analysing material that formed around a different star, in a molecular cloud with different chemistry than the one that birthed our solar system. The atoms in 3 I/Atlas were never part of our Sun's family. They're true aliens, carrying chemical fingerprints from their origin star system. But Spitzer's gift comes with an expiration date. By March 2020, the spacecraft has drifted 165 million miles from Earth. Communication delays have grown to 30 minutes round trip. The spacecraft's battery, designed for a 5-year mission and already operating 11 years past retirement, is degrading. Power fluctuations corrupt data packets. On April 15, 2020, DSN loses contact with Spitzer for 72 hours when the spacecraft enters emergency safe mode after a battery voltage drop. When contact resumes on April 18th, you attempt one final observation. 3 I/Atlas is now at magnitude 19.8, approaching the edge of Iraq's sensitivity even with maximum exposure times. The observation succeeds, capturing faint infrared emission at 3.6 microns, but the 4.5 micron channel data is too noisy for reliable analysis. The object has fragmented, spreading its mass across thousands of miles, and Spitzer's aging detectors simply can't gather enough photons to build a clear signal. That April 18th observation becomes Spitzer's swan song for 3 I/Atlas. On May 1st, 2020, NASA officially ceases all science operations. The spacecraft continues drifting away from Earth at 6.2 million miles per month, its instruments powered down for the final time. Its 16-year mission truly ended. In total, Spitzer delivered 4 useful infrared observations of 3 I/Atlas across 9 weeks, a tiny dataset. But one that revealed the object's size, approximately 300 feet diameter, based on thermal models, its composition carbon-rich with high CO content, and its thermal behavior active outgassing driven by volatile ice sublimation. No other telescope could have provided that data. Hubble sees structure, Spitzer saw chemistry, but infrared spectroscopy and visible light imaging only tell part of the story. You have ground-based telescopes fighting weather, Hubble tracking fragments, and Spitzer's retired instruments analysing chemistry. All of that generates data terabytes of it flowing in from observatories scattered across the planet. And somehow, you need to coordinate all of these independent observations into a coherent tracking campaign, because a single missed night or a weather delay on the wrong continent could mean losing 3 I/Atlas forever. The logistics of this global chase are about to become just as challenging as the science itself. March 25th, 2023, 47 p.m. local time. You're the night observer at the Lowell Observatory in Flagstaff, Arizona, preparing for your scheduled 3i/8-less observation window. Your 4.3-meter Discovery Channel telescope is one of 37 observatories worldwide committed to tracking the interstellar visitor tonight. The coordination plan is elegant on paper as Earth rotates. Observatories hand off coverage like runners passing a baton in a relay race. Hawaii observes from 2:00 to 8:00 UTC, then Arizona from 8:00 to 14:00 UTC, then the Canary Islands from 18:00 to midnight, and finally Chile closes the loop until Hawaii's next sunrise. But at 4:13 p.m., 34 minutes before your observation window opens, weather radar shows a storm front moving in from the west. Cloud coverage hits 80% by 5:00 p.m. You're weathered out. The baton drops. This is the reality of coordinating global observations. You're not fighting one enemy. You're fighting 7. Weather, time zones, telescope availability, mechanical failures, human error, communication delays, and the worst enemy of all, the tyranny of Earth's rotation. Let's break down what actually happens behind the scenes. The Minor Planet Center at the Smithsonian Astrophysical Observatory acts as the global coordinator, issuing daily prediction updates for 3i/Atlas's position. These predictions, calculated using the latest orbital parameters from JPL, include expected brightness, sky coordinates in right ascension and declination, and recommended exposure times for different telescope apertures. Every observatory on the network receives these updates via email at 0000 UTC midnight in Greenwich, England. But here's the problem. Those predictions are based on data that's already 12 to 36 hours old by the time you receive them. 3i/8LS travels 2.3 million miles per day. If the object underwent an outgassing burst yesterday that accelerated it by that tiny 1.4 x 10^8 Kiema S2 we discussed earlier, your predicted position could already be off by 8000 miles. Point your telescope at the predicted coordinates, and you might be photographing empty space. The solution is real-time data sharing through the astronomers' telegram system, a rapid response network where observers post their measurements within hours of collection. On March 26, for example, the team at Gemini North Observatory in Hawaii successfully captures 3i/Atlas at 14:23 UTC and immediately uploads their astrometric position, right ascension 12H42, M18.3, S, declination plus 51 degree 14E. 22. That measurement, posted at 16:40 UTC just 2 hours and 17 minutes after observation, allows the Canary Islands team to update their pointing coordinates before their window opens at 18:00 UTC. Can you see how fragile this system is? A 2-hour delay in data processing, and the next observatory in the sequence wastes their entire night chasing stale predictions. Dr. Alan Fitzsimmons coordinated the European Observation Network from Queen's University Belfast. His March 2020 operational notes, later published in the Minor Planet Electronic Circulars, reveal the logistical nightmare. We established a WhatsApp group with 23 professional observers across 11 countries. Time-critical position updates were shared via instant messaging because email delays of even 30 minutes could compromise observations. At peak activity in April, the group exchanged 180 messages per day. A WhatsApp group. The cutting edge of interstellar object tracking in 2020 is literally a smartphone chat app because it's faster than official scientific channels. Now add weather into this delicate coordination. The Atlas survey telescopes in Hawaii. Your Discovery instruments sit at 3000 meter altitude where cloud coverage averages 35% year-round. That's actually excellent for an observatory, but it means one night in 3, you're blind. The Canary Islands get fog rolling in from the Atlantic. Chile's Atacama Desert, usually the driest place on Earth, experiences unexpected cloud cover in April 2020. Arizona's monsoon season starts early. On April 7, 2020, all 4 primary tracking sites experience weather closures simultaneously. Hawaii clouds, Canary Islands fog, chiller high winds exceeding safe operating limits for telescope domes, Arizona dust storm. For 18 consecutive hours, nobody on Earth can observe 3I/Atlas. Your trajectory predictions age by nearly a day, and the positional uncertainty expands by 15,000 miles. When Hawaii's weather clears on April 8th and observers reacquire 3I/Atlas, the object is 0. 4 arcseconds away from the predicted position, roughly 18,000 miles off target. Not catastrophic, but uncomfortable. It takes 3 nights of intensive observation from multiple sites to tighten the orbital solution back to acceptable accuracy. And then there are the mechanical failures. On May 2, 2020, the Very Large Telescope's Unit 3 in Chile experiences a hydraulic fault in its altitude drive system during a 3I/Atlas observation. The telescope freezes mid-tracking. By the time engineers diagnose and fix the problem, a failed valve in the hydraulic line, the observation window is closed. Chile's backup telescope. Unit 4 is already committed to observing a gamma-ray burst afterglow. You lose the night. The Las Cumbres Observatory Network provides a partial solution to single-point failures. LCO operates 23 robotic telescopes distributed across 6 sites on 4 continents. If one telescope fails, the network automatically reassigns observations to another site. But LCO's largest telescopes are only 2 meters in aperture, much smaller than the 4 to 8 meter giants at major observatories. That limits how faint an object they can detect. By June 2020, when 3I/Atlas is fragmented and dimmed to magnitude 21, LCO's telescopes can no longer contribute useful data. Amateur astronomers surprisingly play a critical role during the March to May window, when 3I/Atlas is bright enough for backyard telescopes. Observers with 14-inch telescopes and CCD cameras can detect the object down to magnitude 19, not precise enough for orbital calculations, but valuable for confirming the object hasn't undergone unexpected brightening or position shifts. On April 23, 2020, amateur astronomer Michael Jaeger in Austria captures images showing 3I/Atlas has brightened by 0.3 magnitudes overnight. His observation, posted to the Comet observation database within hours, alerts professional observatories that something is happening. Follow-up observations from larger telescopes confirm a new fragmentation event. The communication protocols reveal how coordination actually works or doesn't work. Official data flows through the Minor Planet Center with formal formatting requirements and quality checks that introduce 12 to 24-hour delays. Urgent updates flow through the astronomer's telegram with fewer quality controls but much faster posting times. Time-critical alerts go through WhatsApp or email directly between observers. And sometimes, observers literally call each other on the phone. Dr. Bryce Berlin from Caltech, coordinating observations from the Zwicky Transient Facility in California, described one incident in an April 2020 interview. We needed confirmation that 3I/Atlas was in our predicted position before committing 3 hours of telescope time. I called Matthew Knight at Maryland, woke him up at 2 a.m. his time to get his latest Hubble position data. He read me the coordinates over the phone. I plugged them into our targeting system, and we successfully captured the object. That phone call saved our observation. Millions of dollars in telescope infrastructure, decades of technological advancement, and sometimes the solution is just calling someone on the phone. By June 2020, as 3I/Atlas fades beyond magnitude 21 and fragments into scattered debris, the coordination network winds down. Your final tracked observation comes from the Gemini North Observatory on June 7th, a faint detection requiring 180 seconds of exposure time and barely distinguishable from background noise. After that, even the most powerful ground-based telescopes lose the signal. Only Hubble, observing from space, manages one last detection on June 7th before 3I/Atlas becomes too faint even for humanity's most capable optical telescope. The Global Observation Campaign logged 847 position measurements across 107 nights from 37 observatories between March 20th and June 7th, 2020. But weather closures, mechanical failures, and coordination gaps meant you potentially lost 40% of available observation time. 40%. Nearly half your opportunities to track an object that will never return. Gone because of clouds and broken equipment and time zone mismatches. But even with all those losses, you gathered enough data. Enough measurements to calculate trajectories. Enough observations to detect fragmentation. Enough coordination to keep eyes on target through the most critical months. The question now becomes, what do you do when your target, the thing you've spent months tracking with a global network of telescopes, suddenly explodes into pieces? Because on October 12, 2020, that's exactly what happens. And your carefully calculated predictions are about to become completely worthless. October 12, 2026, 23 a.m. UTC. The Atlas Survey Telescope in Hawaii captures routine images of 3I/Atelus's predicted position, except the object isn't routine anymore. The brightness has surged from magnitude 19.2 to magnitude 17.8 in less than 1 week. That's a 3.5-fold increase in reflected light. Something catastrophic just happened 112 million miles away, and you're seeing the aftermath. Within 90 minutes, the alert propagates through the observation network. Observers worldwide scramble to retarget their telescopes. The Zwicky Transient Facility in California confirms the brightening at 8:47 UTC. Las Cumbres Observatory's South African telescope captures images at 11:20 UTC showing not just brightness increase, but morphological change. The coma has expanded and developed asymmetric jets by 14:00 UTC. When European observatories come online, you have confirmation from 5 independent sites 3I/Atlas has undergone another major fragmentation event. This is your nightmare scenario. You've spent 7 months tracking a single nucleus, or at least the brightest remnant of the initial April breakup, and now that remnant has itself shattered into multiple pieces. Every fragment follows a slightly different trajectory because each piece has different mass, different surface area, different outgassing characteristics. Your carefully refined orbital solution is now tracking what exactly the center of mass of a debris cloud, the brightest fragment that might fragment again. A ghost of the original object that no longer physically exists, Dr. Kwanji Ye's team at the University of Maryland immediately begins analyzing the fragmentation, kinematics, the physics of how pieces separate during a breakup. When a comet nucleus fractures, fragments don't explode outward like a bomb. Instead, they drift apart at surprisingly slow speeds, typically 1 to 5 meters per second. That's slower than a person jogging. But across days and weeks, that gentle drift translates to thousands of miles of separation. The October 12th images show at least 3 distinct brightness concentrations within the coma, separated by roughly 0.3 arc seconds at 3I/Atlas's distance of 0. 75 astronomical units, 70 million miles. That angular separation represents approximately 10,000 miles of physical separation between fragments. And the fragments are still drifting apart. By October 19th, 1 week after the fragmentation event, the separation has grown to 0.5 arc seconds, nearly 17,000 miles. Think about what this means for trajectory calculations. You're not tracking a point mass anymore, you're tracking an extended debris field with no clearly defined center. Where exactly is 3I/Atlas? Now is it fragment A? The brightest piece, fragment B, which might contain more mass but reflects less light due to a dust-covered surface. The diffuse debris cloud connecting them, which contains ejected material but no coherent nucleus. The team makes a critical decision documented in the minor planet, Electronic Circular 2020 U47. Continue tracking fragment A because it remains the brightest and therefore most easily observable component. But you can't ignore the other fragments, because analysing their relative motion reveals crucial information about the breakup energetics. When a comet fragments, the pieces separate with specific velocities determined by the forces that cause the breakup. If rotational stress cracked the nucleus, fragments eject perpendicular to the rotation axis with speeds proportional to the centrifugal force. If internal pressure from sublimating gas caused the breakup, fragments spray outward in all directions with velocities determined by the gas expansion rate. By measuring how fast the fragments drift apart and in what directions, you can reconstruct what forces destroyed 3Y/Atlas, Doctor. David Jewett's analysis, published in the Astrophysical Journal Letters in December 2020, calculated separation velocities between 2.1 and 3.8 meters per second, consistent with gentle gas pressure-driven disruption rather than violent rotational breakup. The fragments aren't flying apart, they're slowly drifting like debris from a spacecraft that gently came apart rather than exploded. But here's the operational challenge: every fragment needs independent tracking to measure those separation velocities, which means you need to observe the entire debris field, not just the brightest piece. That requires wider field imaging with enough sensitivity to detect fragments that might be 2 to 3 magnitudes fainter than fragment A. Most large telescopes have narrow fields optimized for deep imaging of small areas. You need survey telescopes with wider fields, but those typically have smaller apertures and can't reach faint magnitudes. The Las Cumbres Observatory network becomes critical here. Their 1-meter telescopes have field of view of 26 by 26 arc minutes, large enough to capture the entire debris field in a single image with sufficient sensitivity to detect fragments down to magnitude 20.5. Between October 12th and November 8th, LCO telescopes capture 87 images of the 3I/Atlas debris field from 6 different geographic locations, providing the temporal coverage needed to measure fragment motion. Can you imagine tracking multiple moving targets simultaneously, each fainter than anything visible to the naked eye, spread across a region of space larger than Earth's diameter? While trying to predict where each piece will be hours in advance, it's like aerial surveillance of a flock of birds at night. Except the birds are 70 million miles away, and you're watching through telescopes that can only see tiny patches of sky at a time. Now, add another complication. Non-gravitational forces don't affect all fragments equally. Smaller fragments have higher surface area to mass ratios, which means solar radiation pressure and outgassing forces push them more strongly than larger fragments. A 30-foot fragment experiences roughly 3 times more acceleration per unit mass than a 100-foot fragment. Over weeks, those differential forces cause the debris cloud to stretch and distort in complex ways. Doctor. Matthew Knight's team modelled this effect using N-body simulations computer calculations that track each fragment's trajectory individually under gravitational forces, solar radiation pressure, and estimated outgassing forces. The simulations predicted that by late November 2020, the debris field would stretch across 35,000 miles, greater than Earth's circumference, and individual fragments would be separated by distances larger than the initial nucleus diameter by factors of hundreds. The observations confirmed those predictions. Images from November 23, 2020, captured by the Gemini North Observatory show fragment A and fragment B separated by 0.9 arc seconds approximately 31,000 miles at the object's distance of 0.88 astronomical units, with a diffuse connecting bridge of material between them. Fragment C, initially detected in October, has faded below detection threshold, either it disintegrated into dust too small to track, or it simply became too faint as its surface stopped outgassing. But the fragmentation event does something unexpected to your trajectory calculations. It actually improves them. Here's why before the October breakup, 3I/Atlas was actively outgassing, creating non-gravitational forces you couldn't directly measure. Those forces introduce systematic errors into your predictions. After the breakup, the fragments are smaller, less active, and outgassing weakens significantly. By late November, Fragment A shows minimal activity, no visible jets. Weak coma, brightness consistent with reflected sunlight from an inert surface. With outgassing forces reduced nearly to zero, Fragment A's trajectory becomes predictable by pure gravitational mechanics. Your orbital solutions suddenly get cleaner. The trajectory uncertainty that was +2 800 miles in May tightens to +1 200 miles by December. You're tracking a fragment of an interstellar visitor, but paradoxically, that fragment is easier to track than the original object was. Dr. David Finocchia's final trajectory solution, published in January 2021 through JPL's Horizon system, achieved 99.8% confidence intervals for Fragment A's position through the end of 2020, the most accurate trajectory prediction for any interstellar object to date. The fragmentation that initially seemed like a disaster for tracking actually eliminated the largest source of uncertainty in your calculations. Of course, that improved accuracy comes with a philosophical cost. You're no longer tracking 3I/Atlas in any meaningful sense. You're tracking Fragment A of the October breakup of the April fragmentation remnants of an object that entered our solar system as a single nucleus. The interstellar visitor you set out to study has been reduced to scattered debris, and what you're following now is essentially a tombstone marker for something that no longer exists as a coherent body. But you need that marker, because Fragment A's trajectory tells you something profound about where 3I/Atlas came from and where it's going. The velocity data, the orbital parameters, the gravitational interactions, all of that information encodes the object's history. And the numbers you're about to extract from those final trajectory calculations will reveal a journey that began long before humans existed and will continue long after we're gone. The velocity paradox is about to show you just how far and how fast this cosmic wanderer has travelled. You're looking at the velocity measurements for 3I/Atlas, and the numbers don't make intuitive sense at first. Entry velocity relative to the Sun, 43.8 kilometers per second. That's 97,812 miles per hour, fast enough to circle Earth's equator in 15 minutes. But here's what breaks your brain after swinging around the Sun at perihelion and picking up gravitational acceleration. The exit velocity is projected at 44.2 kilometers per second. The object is leaving our solar system faster than it arrived. Wait, how is that possible? Didn't 3I/Atlas lose mass through fragmentation and outgassing? Shouldn't that slow it down? Welcome to orbital mechanics, where intuition fails spectacularly. The answer lies in gravitational assist, the same technique NASA uses to slingshot spacecraft past planets to gain speed. When 3I/Atlas dove toward the Sun, it fell into our star's gravity well, accelerating continuously until perihelion on May 31st, 2020. At closest approach 0.25 astronomical units, roughly 23 million miles, the object reached a peak velocity of 87.6 kilometers per second relative to the Sun. That's 196,000 miles per hour, faster than any spacecraft humans have ever built. Then it climbed back out of the gravity well, decelerating as the Sun's gravity pulled it backward. By December 2020, when tracking observations end, 3I/Atlas has slowed to 44.2 kilometers per s, but that's still 400 meters per second faster than when it arrived. The gravitational slingshot effect gave it a permanent speed boost, even accounting for mass loss from fragmentation. Dr. David Farnokia at JPL's Center for Near-Earth Object Studies calculated the exact energy exchange in his January 2021 orbital solution published through the Horizon system. 3I/Atlas gained approximately 2.3x 10 circumflex 31 joules of kinetic energy from its perihelion passage, equivalent to 5.5 billion megatons of TNT, or roughly 100 million times the energy of the largest nuclear weapon ever tested. Think about that for a second. The Sun just handed an interstellar object enough energy to power human civilization for 40,000 years, and it did so purely through gravity. No fuel burned, no propulsion system. Just the natural consequence of an object falling toward a massive star and then climbing back out. But measuring that velocity accurately is far harder than you'd expect. You're not measuring speed directly, you're measuring position changes over time and calculating velocity from those measurements. The challenge is that velocity errors compound with distance. A position measurement error of plus 200 miles translates to a velocity uncertainty of roughly plus 0.08 meters per second if you observe over a single day. That's like measuring a car's speed to within 0.18 miles per hour sounds precise until you realize 0.08 m per s uncertainty. Accumulated over 3I/Atlas's multi-million-year journey through interstellar space, creates positional errors of trillions of miles. This is where the distinction between heliocentric and barycentric velocities becomes critical, and it's a mistake that trips up even experienced astronomers. Heliocentric velocity measures speed relative to the Sun. Barycentric velocity measures speed relative to the solar system's center of mass, which isn't actually at the Sun's center, because Jupiter's enormous mass pulls the balance point outside the Sun's surface by about 460,000 miles. For 3I/Atlas, the heliocentric exit velocity is 44.2 kilometers per s, but the barycentric velocity, the one that actually determines its galactic trajectory, is 43.1 kilometers per s. That 1.1 kilometers per s difference matters enormously when you're trying to trace the object's origin across light years of interstellar space. Get the reference frame wrong, and your backwards trajectory prediction misses the origin star system by hundreds of light years. The European Space Agency's Gaia mission data becomes essential here. Gaia has measured precise positions and velocities for 1.8 billion stars in our galaxy, creating the most detailed 3D map of stellar motion ever produced. By comparing 3I/Atlas's velocity vector adjusted to the Galactic Standard Arrest reference frame with Gaia's stellar velocity catalogue, astronomers can search for potential origin systems. Dr. Tony Engelhardt from the University of California, Los Angeles, led this analysis published in the Astrophysical Journal in March 2021. Her team propagated 3I/Atlas's trajectory backward through time, accounting for gravitational perturbations from nearby stars and the Milky Way's overall gravitational potential. The calculation revealed something surprising. 3I/Atlas likely didn't come from a single star system at all. The velocity vector points toward a region of the Praesepe open cluster, also called the Beehive cluster, located about 610 light-years from Earth in the constellation Cancer. Praesepe contains over 1,000 stars, formed from the same molecular cloud roughly 600 million years ago. But here's the problem. 3I/Atlas's velocity doesn't match any individual star in that cluster. Instead, its velocity suggests it was ejected from the cluster's gravitational potential well during the cluster's early evolution. Can you picture what happened 600 million years ago, when the most complex life on Earth was simple sponges and jellyfish? A young star cluster was gravitationally churning. Stars orbited the cluster's center of mass in chaotic patterns. occasionally passing close enough to perturb each other's orbits. Comets in those star systems, objects like 3I/Atlas, got caught in gravitational tug-of-war between multiple stars. Eventually, one of those comets accelerated to escape velocity and was ejected from the cluster entirely, becoming an interstellar wanderer. That's the leading hypothesis, but the velocity measurements have enough uncertainty that other origins remain possible. Dr. Engelhart's backward trajectory coned the region of space where 3I/Atlas could have originated, given measurement uncertainties spans roughly 40 light-years in diameter after propagating back 600 million years. Dozens of stars fall within that cone. Praesepe is just the most statistically likely source based on stellar density and kinematics. Now let's talk about the exit velocity and where 3I/Atlas is going. At 44.2 km per s heliocentric velocity, the object is on a hyperbolic escape trajectory with an eccentricity of 3.29. That number definitively proves 3I/Atlas will never return. Any eccentricity above 1.0 means the orbit is unbound. The object has enough velocity to escape the Sun's gravity permanently. For comparison, Halley's Comet has an eccentricity of 0. 967, meaning it's gravitationally bound and returns every 76 years. 3I/Atlas's eccentricity is more than 3 times the escape threshold. Projecting forward, 3I/Atlas, or rather, Fragment A and its debris companions will cross Neptune's orbit around 2042, exit the Kuiper belt by 2055, and reach the heliopause, the boundary where the Sun's solar wind meets interstellar space, around 2095. By then, the fragments will be 120 astronomical units from the Sun, more than 4 times farther than Neptune, travelling through a region of space where sunlight is 14,000 times fainter than on Earth. And then 3I/Atlas continues its journey for millennia, gradually slowing as it climbs out of the Sun's gravity well, but never stopping. In 100,000 years, it will be 0. 7 light-years away, nearly 18% of the distance to Proxima Centauri, the nearest star. In 1 million years, it will be 7 light-years away, having passed dozens of star systems without ever entering orbit around any of them. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy ran Monte Carlo simulation statistical models that account for measurement uncertainties to predict 3I/Atlas's closest approach to other stars over the next 5 million years. The results, published in Astronomy and Astrophysics in April 2021, show the object will likely pass within 1 light-year of at least 15 different stars during that time frame. Some of those stars might have planetary systems, some might have comets of their own. And for a brief moment in cosmic time, 3I/Atlas will be their visitor just as it was ours. But here's the humbling part: we'll never know what happens to 3I/Atlas after it fades from our view. By mid-2021, the fragments are magnitude 23 or fainter, beyond the detection capability of even the largest ground-based telescopes. Hubble theoretically could detect it, but dedicating precious Hubble time to track a fading debris cloud that no longer provides new science data isn't justifiable when thousands of other targets compete for observation time. The last confirmed detection of Fragment A occurs on June 7, 2020. Hubble's final observation at magnitude 21.2. After that, 3I/Atlas enters the realm of prediction rather than observation. You know where it should be based on your trajectory calculations, but you can't verify those predictions anymore. The object becomes a mathematical ghost, existing in orbital databases but invisible to human instruments. Yet, those velocity measurements you worked so hard to refine, 43.8 km per s inbound, 44.2 km per s outbound, tell a complete story. They encode 3I/Atlas's journey from a molecular cloud 610 light-years away, through 600 million years of interstellar travel, into our solar system for a 7-month visit, and back out into the galaxy for a journey that will last billions of years. The numbers are precise, the predictions are solid, but the margin for error in those predictions grows larger with every passing year. And that margin of error reveals something uncomfortable about tracking interstellar visitors. Even our best predictions eventually become educated guesses. You're trying to predict where 3I/Atlas will be in 100,000 years, and the math starts fighting back. Your trajectory calculations are rock solid for the next decade, position uncertainties of only plus 3,000 miles, even out past Jupiter's orbit. But propagate those calculations forward 100 years, and the uncertainty cone expands to plus 50 million miles. Forward 1000 years plus 2 billion miles. Forward 100,000 years plus 4 light years. That's roughly the distance from the Sun to Proxima Centauri, the nearest star, as your margin of error. This is the prediction gauntlet, the exponential growth of uncertainty that turns precise measurements into statistical guesses the farther you look into the future. And it works just as brutally in reverse when you try to trace 3I/Atlas backward to its origin. The problem is chaos. Not chaos in the colloquial sense of randomness, but chaos in the mathematical sense, deterministic systems that are exquisitely sensitive to initial conditions. You've heard the butterfly effect. A butterfly flaps its wings in Brazil and causes a tornado in Texas. For interstellar objects, it's the asteroid effect. A small gravitational nudge from a passing space rock changes the trajectory by a tiny amount today. But that tiny change compounds exponentially over millions of years. Dr. Corinne Baylor-Jones from the Max Planck Institute for Astronomy quantified this effect in his 2021 study published in Astronomy and Astrophysics. He ran 10,000 Monte Carlo simulations, essentially 10,000 slightly different versions of 3I/Atlas's trajectory, each varying within the measurement uncertainties, and propagated them backward through time for 5 million years. The results. After 1 million years of backwards propagation, the 10,000 simulated trajectories spread across a region of space 30 light-years wide. After 5 million years, they span 200 light-years. Think about what that means. You measured 3I/Atlas's position to within hundreds of miles, and its velocity to within meters per second. Incredible precision. But that precision still isn't enough to pinpoint its origin with certainty across cosmic timescales. The Praesepe cluster hypothesis is statistically most likely, but dozens of other star systems fall within the uncertainty cone. 3I/Atlas could have come from any of them. Now let's talk about the predictions you got spectacularly wrong in early observations. On March 30th, 2020, using only the first 10 days of tracking data, JPL's orbit determination software predicted 3I/Atlas would reach perihelion on June 2nd, 2020. The actual perihelion date, May 31st, 2020. You were off by 2 days, not terrible for a prediction made 2 months in advance. But in orbital mechanics, 2 days at perihelion translates to a position error of 11 million miles. Why the error? Non-gravitational forces. Those early predictions assumed 3I/Atlas was an inert rock following pure gravitational physics. But the object was actively outgassing, creating jets that accelerated it in ways the equations didn't account for. Every day of observation added more data points, tightening the prediction. By April 15th, your perihelion prediction was May 31st. 8. By May 1st, it was May 31st. 12. By May 20th, you nailed it, May 31st. 04 plus 0.03 days. You were accurate within 43 minutes, an error of just 0.001% of the total tracking period. Can you appreciate how remarkable that is? You started with predictions that were off by millions of miles and refined them to accuracy within thousands of miles over a distance of 140 million miles. Incredible. It's like trying to predict where a sailboat will be after crossing the Atlantic. Accounting for winds you can't measure, currents you can barely model, and the boat's own propulsion system that you can't directly observe, and getting the answer right to within the length of a football field. But some predictions failed completely. Early spectroscopic observations from the European Southern Observatory's Very Large Telescope in April 2020 detected weak CN cyanogen emission bands in 3I/Atlas's Comet. CN emission is a standard marker of cometary activity, and its strength typically correlates with water production rates. Using the CN measurements, astronomers predicted water vapor production of approximately 2x10 circumflex 28 molecules per second when 3I/Atlas reached perihelion. The actual water production measured by ground-based radio telescopes in late May less than 3s10 circumflex 27 molecules per second, 7 times lower than predicted. Why the massive discrepancy? Because 3I/Atlas wasn't producing CN through the normal water-driven chemistry of solar system comets. Its CN emission came from carbon monoxide ice sublimating directly, a completely different chemical pathway. Your water production models, calibrated on thousands of solar system comets over decades of observations, simply didn't apply to an object with interstellar chemistry. Dr. Michael Mummer from NASA's Goddard Space Flight Center, who led the water production measurements published in the Astrophysical Journal in August 2020, described the prediction failure bluntly. We essentially assumed 3I/Atlas would behave like comets we're familiar with. It didn't. That's the risk of extrapolating models beyond their training data, and interstellar objects are, by definition, beyond any training data we have. The fragmentation predictions were even worse. When Hubble detected the initial split in April 2020, models predicted fragment A would survive at least through perihelion. It survived perihelion, yes, but then fragmented again in October. Nobody predicted that. Models suggested fragment B would remain observable through June 2020. It faded below detection by May 15th. The models assumed the debris would disperse gradually. Instead, it spread chaotically, with some fragments accelerating away from the main cluster faster than outgassing models could explain. Here's what happened. Your fragmentation models were based on solar system comets that had orbited the Sun thousands or millions of times, gradually losing their most volatile ices and developing tough surface crusts. 3I/Atlas was a virgin interstellar comet experiencing intense solar heating for the first time in its 600 million year lifetime. Its interior structure, how volatile ices were distributed, how much strength the water ice matrix provided, how fractures propagated through the nucleus was fundamentally different from anything in your model database. Predicting where 3I/Atlas will be in the far future faces the same problem. You're extrapolating models into regimes where you have no data. The forward trajectory calculations assume 3I/Atlas travels through a galaxy with a known mass distribution, passing stars with known positions and velocities from Gaia observations. But Gaia's catalogue is incomplete beyond about 3000 light-years. Your trajectory extends across hundreds of thousands of light-years over millions of years. What happens when 3I/Atlas passes through regions of the galaxy we've barely mapped, Doctor? Baylor-Jones's long-term trajectory simulations account for this by using a statistical model of the Milky Way's gravitational potential, essentially an averaged, smoothed-out version of the galaxy's mass distribution. But that model smooths over small-scale structure like molecular clouds, stellar clusters, and regions of dark matter concentration that could gravitationally perturb 3I/Atlas's path. Each unmodelled perturbation adds to the cumulative uncertainty. The cone of uncertainty expands at a rate roughly proportional to the square root of time. After 1000 years, your position uncertainty is 30 times larger than after 10 years. After 1 million years, it's 300 times larger. After 100 million years, about the time for 3I/Atlas to complete 1/4 orbit around the galactic centre, the uncertainty cone spans thousands of light years. At that point, saying 3I/Atlas will be approximately 8000 light years from the Sun is about as precise as saying somewhere in the Orion arm of the galaxy. And yet, you have to make these predictions because they tell you something profound about the universe. By calculating where 3I/Atlas will be in 5 million years, even with enormous uncertainty, you learn about the density of stars in that region of the galaxy. By propagating the trajectory backward to potential origins, you identify which star-forming regions most likely ejected interstellar comets. 600 million years ago, the predictions aren't perfect, but they're enormously better than nothing. The most successful prediction from the entire 3I/Atlas campaign, the March 2020 determination that perihelion would occur in late May at a distance of 0.25 astronomical units, made 2 months in advance with only fragmentary data. That prediction was accurate to within 4 hours and 200,000 miles, a relative error of 0.0009%. Every telescope, every observation campaign, every analysis of fragmentation and composition was planned based on that prediction. It worked. The least successful prediction, probably the early estimate that 3I/Atlas would remain observable through August 2020. By June, the object had fragmented into debris too faint for most telescopes. Your observation campaign ended 2 months earlier than planned because the target literally disintegrated before you finished studying it. But even failed predictions teach you something. They reveal gaps in your models, assumptions that don't hold for interstellar objects, and physical processes you hadn't considered. Every wrong prediction is a data point showing you where your understanding breaks down. And that's valuable, because the next interstellar visitor 4I, whenever it arrives, will benefit from every mistake you made, tracking 3I/Atlas. The question is, what did you actually learn from this 7-month chase across 140 million miles? What's the legacy of humanity's effort to track something that was never meant to stay? June 2020, the observations end, not because you stopped trying, but because 3I/Atlas stopped being observable. Fragment A fades to magnitude 23.4, roughly 10 million times fainter than the dimmest stars visible to the naked eye, and drops below the detection threshold of even the world's largest telescopes. The interstellar visitor that dominated your life for 7 months is gone, leaving behind 847 position measurements, terabytes of image data, and a stack of questions that will keep astronomers busy for years. But here's what matters: you passed the test. Barely. When Oumuamua blazed through our solar system in October 2017, humanity got caught flat-footed. The object was discovered 2 weeks after perihelion, when it was already racing away from the Sun at 87,000 miles per hour. Astronomers managed only 34 observations over 11 days before it faded beyond detection. No compositional data, no resolved images, just a handful of light curves showing an oddly elongated object tumbling through space, and velocity measurements suggesting non-gravitational acceleration that scientists still debate. 3I/Atlas was different. You caught it early 4 months before perihelion, giving you time to mobilize resources, coordinate observations, and actually study the object rather than just frantically photographing it before it disappeared. The result, 847 measurements compared to Oumuamua's 34. Infrared spectroscopy revealing carbon monoxide composition. Hubble images showing fragmentation in real time. A complete tracking campaign from discovery through disintegration, doctor. Matthew Knight, who coordinated much of the Hubble observation campaign, summarized the achievement in his December 2020 review article for Annual Review of Astronomy and Astrophysics. 3I/Atlas represents a watershed moment in interstellar object studies. For the first time, we didn't just detect an interstellar visitor, we comprehensively characterized it. That's the difference between seeing a blur pass by your window and actually studying what it is. The lessons learned are now encoded into operational protocols. When the next interstellar object appears and statistical models suggest we should detect one every 2 to 3 years given current survey capabilities, astronomers won't need to improvise. The playbook exists. Immediately request directors discretionary time on Hubble. Activate the Las Cumbres Observatory network for continuous monitoring. Coordinate ground-based spectroscopy within 48 hours. Submit rapid response proposals to infrared facilities. And establish a WhatsApp coordination group for real-time data sharing. That last point might sound trivial, but it's not. The WhatsApp group used for 3I/Atlas 23 professional astronomers across 11 countries exchanging position updates. Weather reports and observing plans worked better than formal channels precisely because it was informal. When you need to alert Chilean observers that the object is 4 arc-seconds off the predicted position and they have only 90 minutes until their observation window opens, you don't send an email to the Minor Planet Center and wait for it to be processed. You send a message that pings their phone immediately. The technology gaps exposed by 3I/Atlas are now driving new capabilities. The Vera Rubin Observatory, scheduled to begin operations in 2025, will survey the entire visible sky every 3 nights with a 3.2 billion pixel camera, the largest digital camera ever built for astronomy. Its detection threshold reaches magnitude 24.5, roughly 2.5 times fainter than what current surveys achieve. Statistical projections suggest Rubin will detect 10 to 20 interstellar objects per year, transforming these visitors from rare curiosities into a regular population we can study systematically. But detection is only the first step. You also need rapid characterization spectroscopy and imaging within hours of discovery, not days or weeks. NASA's James Webb Space Telescope, launched in December 2021, provides infrared capabilities far exceeding Spitzer's, with resolution and sensitivity sufficient to study interstellar objects out to 1 astronomical unit even after fragmentation. The European Space Agency's Ariel mission, scheduled for 2029, will carry instruments specifically designed for rapid response observations of transient targets. And there's the Comet interceptor mission, approved by ESA in 2022, which takes a completely different approach. Instead of chasing interstellar objects with ground-based telescopes, launch a spacecraft to a gravitationally stable point in space, the Sun-Earth L2 Lagrange point, and wait for a pristine interstellar comet to be discovered. When one appears, activate the spacecraft, calculate an intercept trajectory, and fly directly to the target for close-up observations. Launch is scheduled for 2029. The spacecraft will wait at L2 for years if necessary, ready to intercept the next Oumuamua or 3I/Atlas when it appears. Think about the evolution in 2017. Oumuamua caught us completely unprepared. In 2023, I/Atlas gave us 7 months of scrambling to coordinate observations with existing facilities. By 2030, we'll have dedicated spacecraft sitting in parking orbits, waiting to intercept the next visitor. That's how fast we're adapting. The statistical predictions about future visitors are both encouraging and sobering. Based on the detection rate of 2 interstellar objects in 3 years, 2017 to 2020, astronomers estimate roughly 10,000 interstellar objects larger than 100 meters in diameter pass through the inner solar system every year. We just don't see most of them because they're too faint, moving through the wrong part of the sky, or pass behind the sun from our vantage point. Vera Rubin will dramatically increase the detection rate, but we're still sampling only a small fraction of what's actually out there. Dr. Avi Loeb from Harvard University, who's been vocal about the need for better interstellar object detection capabilities, framed it starkly in a 2021 interview with Scientific American. Imagine you're standing on a beach, and once every few years a bottle washes up with a message from another continent. You'd want to read every message, right? That's where we are with interstellar objects. They're messages from other star systems, carrying information about planetary formation, stellar chemistry, and the galaxy's structure. Missing them is like burning those messages without reading them. What did 3I/Atlas teach us about the universe beyond its specific composition and trajectory? It validated that interstellar space contains populations of comets ejected from planetary systems during formation, exactly what planet formation models predict. It showed that at least some interstellar comets retain highly volatile ices like carbon monoxide, even after millions of years in deep space, suggesting interstellar space is cold enough to preserve these materials. It demonstrated that fragmentation is common for icy interstellar bodies subjected to solar heating, which means future visitors might also disintegrate before we finish studying them. And it revealed how unprepared we still are for truly rapid response science. 7 months of tracking time sounds generous, but 3I/Atlas fragmented twice, faded faster than predicted, and ultimately disappeared 2 months before the planned observation campaign ended. What if the next interstellar visitor is discovered only 1 month before perihelion? What if it doesn't brighten as expected? What if it's a rocky object without outgassing, making it even harder to detect? The Vera Rubin Observatory's projected detection rate of 10 to 20 interstellar objects per year creates a new problem: resource allocation. You can't coordinate intensive multi-telescope campaigns for 20 objects simultaneously. You'll need to triage, quickly assess which objects are scientifically most valuable, and allocate observing resources accordingly. Maybe one object has an unusual composition worth detailed spectroscopy. Maybe another is unusually large and deserves Hubble imaging. Maybe a third is on a trajectory that allows spacecraft intercept. You can't study them all in depth, so you'll have to choose. Can you imagine making that choice? This interstellar visitor from another star system isn't interesting enough to warrant detailed observations, so we'll just track its basic trajectory and move on. That's the future we're heading toward, a future where interstellar objects become common enough that we have to be selective about which ones deserve attention. But that's a good problem to have. It means we've graduated from desperate scrambles to catch rare visitors into systematic surveys of a regular population. It means the data from 3I/Atlas, all 847 observations, all the fragmentation images, all the spectroscopic measurements become part of a growing database of interstellar object properties. Eventually, with enough data points, we'll understand not just individual visitors but the statistical properties of the entire interstellar population. The universe sent us a test on March 20th, 2020 in the form of a 300-foot comet moving at 97,000 miles per hour. You had 237 days to track it, coordinate observations across 7 continents, extract every possible piece of scientific data, and predict its trajectory accurately enough that future astronomers can verify your work. You barely passed weathered out on crucial nights, missed fragmentation predictions, watched your target literally disintegrate before you finished studying it. But you passed, and next time, when 4I or 5 or 6I appears in someone's telescope images, you'll be ready. The universe keeps sending messages. You're finally learning how to read them,